That's so good. You actually have. Okay, so today we're going to do very briefly chapter 23 on organometallic chemistry, and then we'll be done. So the rest of lectures that we have will be just for review. So bring question things that you have for next time. Okay, so an organometallic compound, maybe not a giant surprise, it's got organo and metallic in it. So it's going to involve a bond between a metal and a carbon. So we normally see in a bunch of different organic molecules is say bromomethane is the polarity of this bond. It's like that, and so we have a partial negative charge on atom like bromine and a partial positive charge on carbon. Another example would be acetone. The oxygen is more electronegative than carbon, so it pulls electron density toward itself. And again, the carbon has a partial positive charge. Because carbon is less electronegative than most of the heteroatoms that we see it bonded to in organic chemistry, like the bromine, oxygen, etc. The opposite is true, though, for metals. So carbon is more electronegative than pretty much all metals. So if we take that same bromomethane example and replace it with any metal, but in this case, I'm going to choose lithium. Now our bond polarity is reversed because our little polarization arrow points to the more electronegative atom. And so on that bond, it's going to point toward the carbon. And that means that the lithium has a partial positive charge. And the carbon has partial negative charge. Or we could actually take it a step further if we say that the electronegativity difference between carbon and lithium is very large, which it is. We can actually kind of pretend that we have an ionic bond rather than a covalent bond. So now we have two ions, one of which is a carbon anion. So because of that lone pair and the negative charge on the carbon, these sort of molecules where we have an alkali metal attached to a carbon, these are very strong nucleophiles and very strong bases. So what do we think of as a strong base? Sodium hydroxide is a strong base, right? We usually use sodium hydroxide in a solution with water. However, if you take something like that molecule, methyl lithium, and react it with water, or try to dissolve it in water, instead react, you actually get methane. So this CH3 is such a strong base that it's going to deprotonate water, which is not a particularly strong acid. So we get methane, that's going to bubble out our solution, and we get lithium hydroxide. And depending on what type of organolithium compound we have, this can be a really violent reaction. So some examples. Of these that we see pretty often, well, as I said, this one, that's methyl lithium. Probably the single most common is this with a butyl group. In butyllithium. And can also do a tert butyl group to give us tert butyllithium. Generally speaking, these sort of compounds where we've got a tertiary anion like that are going to be the more reactive ones. And in fact, this compound is so reactive that it bursts into flames on contact with air. That space. It bursts into flame on contact with air because of the water in the air. That's how intense that reaction is. So even butyllithium, if you spray it out on the bench, it would sort of fizz and pop a little bit just with the water in the air. So when you're using these compounds, you have to use strictly a nitrogen. And yes.
Can we please light something up on our last look?
That's over though.
But we still have to go in for the final. Let's do that. Please.
I know we don't have any of this on campus. Somebody might have butyllithium, but I kind of doubt it.
No, somebody has
I used it in my research though, so. Anyway. Yeah, fun, kind of actually fun to work with. But there was a really famous lab fire at UCLA where a grad student was trying to use a plastic syringe. And you know how they get kind of sticky? She was pulling on the plastic syringe and she pulled too hard, it came out, and the whole bottle of butyllithium got all over her and she died.
Oh my god. Oh,
Yeah.
oh no. I thought it would be like a really cool story.
Oh, no, she died.
I know, I hate those.
They tried to arrest the PI at the lab,
Well,
but for negligence, but like, she should have, like, lab training covers this stuff. She should have known that you don't do that. Anyway, that's a story for another day.
I take those lab quizzes seriously. You know,
Okay, so, clearly we don't use these unless we have to, because they can be potentially dangerous. But an example would be when I say deprotonate weak acids, the term acid is a big stretch. That's an acid. Ready? Okay, so this is THF, tetrahydrofuran, pretty common solvent. Not a compound that one would consider to be acidic by any stretch of the imagination, but it has these two CH bonds on that carbon. Again, they don't look very reactive, right? Even N-butyllithium is a strong enough base to just pull that proton off. So what you end up getting is butane as a side product, because lithium essentially swaps out for a hydrogen. That butane bubbles out of the solution, and then you have this anion, which is stabilized by the lithium, but it's still super reactive. And that's an excellent nucleophile, and so you can do reactions at that point. That sort of acts like almost like the alpha carbon in an enolate. But it's not, there's no resonance stabilization here to make it more stable. It's just because it's such a strong base that it's able to deprotoniate. So essentially, these compounds let us do chemistry at positions that don't look very reactive. And often that's something that we're interested in doing. Okay, so we talked about metals on the left side. Left side? Yes, right, left. Left side of the periodic table. We haven't talked about the transition metal stuff. And so to do that, we have to talk about coordination compounds. And so I'm going to define a coordination You're also gonna see this, called the coordination complex, which is a noun. Complex is a noun in this case. So this means that we have a metal atom in the middle of the molecule. And we've got sort of a sphere of other molecules attached to that metal. We call those ligands. So let's take what looks like a salt, cobalt 3 chloride hexahydrate. And this is something that you might have seen in general chemistry. And you kind of didn't know what the water part was about, you just sort of associated with the molecule. And so you probably would have said that this is made up of a cobalt ion, which has what charge on it, this molecule? Come on, Gen Chem. There's 3 chlorides. So it's got to be a 3 plus to balance the 3 minuses. Okay, so probably looks something like that, right? And that's a good enough explanation for just cobalt 3 chloride by itself. When it's associated with the water molecules, something kind of different happens. So what we actually have is a cobalt atom in the middle. And surrounding it are those 6 water molecules it's associated with.
This, oh, were you about to explain it?
This?
Yeah,
Yes.
sorry.
So you'll notice a couple things here. First of all, there's no charge written on the cobalt, even though we said it's a 3 plus. When we draw molecules like this, the oxidation state is inferred. So you don't have to draw it. How do we infer it in this case? Well, we draw this symbol, which is kind of like a bracket thing. Essentially, it's saying that what we're going to write here applies to molecule. And then we write the anion, or it could be a cation. Usually it's an anion that balances out the charge of the main part of the complex. In this case, it's the 3 chloride. There's one other weird looking part of, well, I imagine this probably looks totally weird, but notice anything about the bonds? So how many bonds does oxygen have when it's neutral? 2. These water molecules already have 2 bonds, right? And so we're making 3 bonds to oxygen, that means it should have a positive charge, right? As it turns out, these are not your typical kind of covalent bond. These are dative bonds. And dative bonds mean we have an unequal sharing of electrons coming from the ligand and sort of reaching out to grab the metal. So another way you could say this is here. There's our water molecule. It's got 2 lone pairs on the oxygen. One of those lone pairs is sort of interacting with, reaching out toward the cobalt in order to give the cobalt more electrons. And so sometimes we also draw those as arrows. No, that should be a different sound. Right? So here's another coordination complex. Anyone heard of cisplatin? Anybody have somebody with cancer in their family? Yeah. This is like the original chemo drug. I don't know about you. That does not look like something I want to put in my body. Hence why chemo is so miserable, because it's poison, basically. Good poison, but the idea is to poison the cancer slightly more than it poisons you. Anyway, so this compound has dative bonds. The way we tell the bond is dative so we can abbreviate this as metal bonded to NH3. If we sort of draw something like this, where we pull the electrons back onto the ligand, we get that. Is that neutral or charged? NH3 with a lone pair, that's neutral. So what if we do the same thing? Chlorine. But this, sorry, I can't see it over there, but yeah, this is charged. This should have a minus charge. So that means that this bond is covalent. I'm not gonna ask you to do this. Just want you to see it. Okay, how many electrons can an atom have before it's full?
8.
8. It was a lie, I'm sorry.
No. 18.
It's actually not 18, but for today, it's gonna be 18. So, one thing you'll notice about this is it's got, even just with the ligands, each donating 2 electrons, that's 12. So we've already broken the octet rule. So why is this possible? Remember SPDF? Different kinds of orbitals. All of the chemistry that we've done is just involving s and p orbitals and sp hybrid orbitals. But transition metals in the middle of the periodic table in the d block have d orbitals. So how many s orbitals are there? Well, there's 1 s orbital. That gives us 2 electrons. How many p orbitals are there? 3. 2 electrons per orbital gives us 6. And then we remember how many d orbitals there are? It's 5. That's 10 electrons. And there's your 18. So it's not that the octet rule is a lie, really. It's that the octet rule works great for atoms that only have s and p orbitals. But once you add d orbitals, you get another 10 electrons. Play with for a total of 18. Okay, so here's a compound that I actually work with a little bit. Anybody remember what Ru is? Ruthenium. Sorry, I'm a little biased, but ruthenium. So how do we figure out how many electrons the ruthenium has? I'm not going to ask you to do this, but essentially you involves knowing that both of the chlorides are negatively charged and the triphenylphosphine ligands are neutral. That means that we have ruthenium with 2 oxidation state. And if you count up electrons in orbitals, you have to look at the periodic table. We'll figure out that that has 6 valence electrons. And then, so the ruthenium itself has 6 electrons, and then each of these ligands is contributing 2 electrons to the ruthenium. So the 3 triphenylphosphine ligands altogether give us 6, two chloride ligands, plus 4. That ends up having a total of 16 electrons.
So must be charged.
Hmm?
It has a charge on the moment.
It doesn't have a charge because the ruthenium, if it did, then I would have to tell you like that. So, but that's not true here. So the ruthenium and the chloride both balance each other, but what the 16 does mean is that if another ligand comes along, say another triphenylphosphine, with those 2 electrons, it wants 2 more. And so if you give this molecule a little bit more triphenylphosphine, that other ligand will attach in order to make ruthenium happy. This is more inorganic chemistry than it is organic chemistry, but also all of the compounds that I've drawn so far do not have metal carbon bonds. So technically they're not organometallic compounds, but you can draw. This is the great thing about it. You can just put random stuff together and make molecules. Let's do about palladium. Let's hydrogens on it. We call these hydride ligands because they behave like the hydride and sodium hydride or something. And then we could have an alkyl group. Do that. You could also have, and this is going to look really freaky, but do stuff like this. So this is actually ethylene. And instead of using a lone pair of electrons to donate to the metal, we don't have a lone pair, but there is a pi bond there. So pi bonds can also donate electrons to metals. This is how polymerization catalysts work. Because you can partially break that pi bond as the metal sort of pulls electrons toward it. That makes the alkene more reactive.
So you said it can act like a native bond? Is that what you said?
Yes. There's a bunch of different ways to draw stuff like that. So the only stuff I'll ask you eventually on the final related to this is just definition kind of stuff. I'm not going to make you like draw structures and stuff. This is the whole course by itself.
Are you talking about 23 in general, or?
Yes. Yeah. But you have to take inorganic first, then take that. We don't have either, so. Can you tell I like this stuff? Sorry.
You did your PhD on
I did, yes. All right, happy Thanksgiving.
Yes.